Nah, it'll capture it all.
Okay, that's really interesting.
So
I don't think we have a chance to.
Okay, well, that's what I'm working on with Duncan and Huang Yu.
That's fun.
And Josh Rosberg.
Yeah.
Okay, everyone, let's get started. I'm very happy to have Max visiting us today from Fermilab. And Max is going to tell us some things about forward physics. Please take it
I
away.
will. Hi, everybody. I'm Max Fieg, coming from the faraway land of Batavia. Here to talk to you about some things I thought about a lot during my PhD. And I hope I can get you excited about forward physics at the LHC. And sort of as a one-slide summary, what I hope I can show you today is that if we answer questions about what's happening in the forward direction at the LHC, so at large pseudo rapidities, sort of what's going down the beam pipe, we can answer big questions about what's going on inside the nucleon structure, inside protons. We can understand what PDFs look like. We can answer some questions about dark matter. We can learn a lot about neutrino scattering and nuclear structure. We can actually learn a lot about what's going on at central experiments at the LHC. And there's connections to Dune, and there's a very nice connection to astroparticle, which I'll talk about. Okay, so sort of the plan for today, I'm going to give you an overview of the standard model and BSM program, and then to go into a little bit more depth on a couple topics, I'm going to talk about a standard model case study and a BSM case study. I just choose two semi-random case studies here, but if there's something else you're thinking about, please ask me and I can tell you more about it. Okay, so what are some of the big questions that I'm going to be thinking about in the back of my mind throughout this talk? So one is dark matter, right? So we're sort of used to the WIMP paradigm. If I have some heavy dark matter, I can get nice freeze out. But with the thermal cross section, I can get the correct freeze out if I think about lighter dark matter masses and very weak coupling. Okay, we're thinking about GeV scale dark matter itself. I'm thinking about the hierarchy problem. So I'm thinking about that there should be some new TeV particles that we haven't seen yet. Where could they be? I'm going to be thinking about neutrinos and neutrino masses. So obviously a very smoking gun of new physics. So we want to study neutrinos a lot. So I'm going to be thinking about neutrinos throughout this talk. And I'm also going to be thinking a lot about the origin of cosmic rays. So we want to know how these cosmic rays are being accelerated. I need to know more about them if I want to learn about something like the KM3 net event or something that's going on at IceCube. I need to know a lot about cosmic rays. Now, if I want to answer any of these questions, I have to deal with QCD. QCD is getting in the way in all of these questions. Really what's going on here, I got some large coupling. So I've got some bag of partons that I have to deal with every time I want to learn anything, some PDFs that I don't really know what they are, and I have to deal with hadronization. I don't know how the hadronization process happens in a very precise way. Of course, we have very good models, but there's still limitations to this. There's also many open questions within QCD. So I'm thinking about BSM and SM. I hope I can get you excited on the SM front. Okay, how do we answer all these questions? The LHC. To me, these are just two cylinders because I'm a theorist. Of course, these are very sophisticated machines. And it reminded me of something I saw when walking around campus today. I saw this crazy sculpture that sort of reminded me of a collision at the LHC. I looked up a little bit about this thing and I found out that this is supposed to reveal the functioning parts of a technological device or indicate a crisis at hand. I think that sort of goes nicely here. Right? This thing is a remarkable machine, and I hope people don't give up on it anytime soon. Okay, but what's going on in my nice cylinder? So usually we're thinking about collisions at high PT. So I've got these two bags of partons, and they're going to collide at some center of mass energy. Now, if I'm thinking about high PT and I'm thinking about heavy particles, these heavy particles are usually going to go in the transverse direction. So if I have some Higgs W or Z, I'm going to take a nice picture of it and learn about what this thing's doing. Or I could have some new TeV scale particle, some new heavy particle that I'm looking for. Now the cross section for some TeV scale production is on the order of picobars. So keep that number in your mind for a couple of moments here. Okay, now so far we've got nothing new yet, but I would say the LHC is far from done. There's new analyses, unexplored final states. We're going to have a whole bunch of upgrades on the hardware and the software side. There's a bunch of intriguing excesses that we want to keep an eye on. And of course, we'll have the high luminosity understanding. But we really want to fully exploit this $5 billion machine. As far as you can tell right now, it will be our best instrument to look for new physics. So I want to make the point that the low PT region is relatively unexplored. Okay, so let's go back to a collision. Okay, so generally, most collisions at the LHC are going to be these low PT soft collisions. So for example, if I have some collision where the parton has a large momentum fraction in one direction and a smaller momentum fraction in the other direction, I'm going to expect this spray in the so-called forward direction. Okay. Now the cross section for these processes is 75 millibars. That's the inelastic cross section. We compare that to picobars. So really most of the particle production is happening in this forward direction, and we're really not looking at it as much as we should. So this forward direction is really housing an intense beam of TeV particles. What do I expect to see here? Lots and lots of hadrons, GeV scale particles, all coming out with an energy of about a TeV. By the way, please interrupt me at any time. This should be understandable and fun for everyone, and it's a lot more fun if it's interactive. Okay, so let's see what's going on in this forward direction a bit closer. So as I mentioned, we're going to get a lot of hadron production. These hadrons are going to come out with some characteristic momenta. So for example, on the x-axis here, I'm showing the theta angle of the hadron coming out and the momentum on the y-axis. And there's some characteristic PT going like lambda QCD. Okay? And generally, the angle of these hadrons coming out is going to be on the order of millirad. It's going perfectly forward, not perfectly, forward. Okay? These hadrons are going to decay. They're going to give me, so if I have a pi zero, I'm going to get lots of photons. If I have pions, kaons, or d mesons, I'm going to get lots of neutrinos of all flavors. And I can also have sort of a factory for BSM production. Tons and tons of hadrons, and even if I have small branching fractions, I can have some BSM particle coming out with a TeV energy. Okay, now the claim is that the forward direction, I don't know how to get rid of that. The forward direction is a treasure trove of physics. Why? Well, one, we can probe BSM directly. So I already mentioned sort of the story about WIMPs and light very weakly coupled dark matter. Where can I get BSM? I can think about hadrons decaying to BSM as some sort of dark matter factory or BSM factory. And I can also be thinking about BSM properties of neutrinos. Okay. Now, if I have some light, very weakly coupled particle, for an unstable particle in the dark sector, it's going to be naturally long-lived. Why? Well, I've got a huge boost. It's relatively light, and I've got very weak couplings. So if I'm thinking in this direction, I should be thinking about long-lived particles. If it's stable, then I should be thinking about looking for hard scattering of some TeV particles with some detector in this forward direction. Okay, there's many examples of things we can look at. I'll talk about a couple of these here. So dark photons, heavy nuclear leptons, ALPS, quarks, dark Higgs, list goes on. Okay. Second thing we can do is we can test QCD under extreme conditions. There's really two question marks of QCD when we think about forward physics. Okay, don't press that button. So there's sort of a mystery of what happens in the initial PP collision. I got some bags of gluons that are essentially colliding. And then I have some mystery of what happens if some neutrino emerges from that collision and scatters inside the detector. So we can answer questions about what QCD is doing on both ends. So as I mentioned, we can probe PDFs via PP scattering, models of hadronization, or nuclear structure via DAS. And there's a really important point here that I'll spell out again in a couple more slides. There's really, really important implications for cosmic ray physics. Why? Well, if I think about in the center of mass frame, 13 TeV, we're all used to that number. But if I boost this to a frame where one of the protons is at rest, then the other one is moving at an order of 100 PeV. I've got some cosmic ray factory. So if I study what's happening in that forward direction, I can learn a lot about what's happening for particle production in cosmic rays in the atmosphere. Okay, and then the third sort of big bullet point that's on mine is neutrino physics. I've got neutrinos of all flavors coming out, and there's a lot we can do with this, as I'll spell out. So the lowest hanging fruit, I would say, is we want to measure the neutrino cross section. At lower energies, below 100 GeV or so, we have tons of experience measuring the cross section, beam dumps. At higher energies, we have neutrino experiments like IceCube measuring the high energy cross section. But in between, we haven't measured the cross section. And this is exactly where the forward neutrino spectra will peak. And moreover, we'll get significant new tau rates and the first direct observation of new tau bar. We expect to see that eventually. Okay. Moreover, we can refine predictions for the prompt neutrino flux at IceCube. I'll spell this out a little bit more and probe BSM properties of neutrinos, non-standard interactions, sterile oscillations, or electromagnetic properties of neutrinos. Okay. Now, let me spell out this cosmic ray factor point a little bit clearer. It's extremely important that we measure what the hadron flux is in the forward direction. Okay. One of the things I care about is I want to know what the pions and kaons are doing in the forward direction. Why? Well, we've got this puzzle in cosmic ray physics called the muon puzzle. There's an excess of muons that's been consistently observed by Pierre Auger and other experiments. So for example, here's the data from Pierre Auger, and here's the default prediction of Pythia. Okay, so we've got some excess of muons. Could it be BSM? Maybe. Is it BSM? Probably not. But if I want any hope at understanding what this, what's happening here, I've got to have a good understanding of what the pions and kaons are doing. Why pions and kaons? There's some hypothesis that if I have some strangeness enhancement, some extra kaons, I can solve this muon puzzle. Okay. So likely it's due to some QCD mismodeling. Moreover, the number of muons is a key observable if I want to extract the species of some cosmic ray that's impinging on the atmosphere. So whether it's a proton or a heavier nuclei. Okay, so that's pions and kaons. The D meson flux is also extremely important. Why? Well, experiments like IceCube, they want to measure the extragalactic flux of neutrinos coming from outside the galaxy. And I expect this to be isotropically distributed across the sky. But there is a expected component of isotropic neutrinos coming from cosmic rays. A cosmic ray impinges on the atmosphere, produces some D meson, and I have some irreducible background of neutrinos that's also isotropic. So I can't intrinsically untangle these two. And unfortunately, we don't know what this flux looks like. That's what this slide was. So here's our predictions. So this big band right here is what we expect the prompt neutrino flux to look like. So kind of no idea. This is a preliminary estimate of what forward measurements can do to refine that understanding of the forward D meson flux. Okay, so big implications for IceCube and KM3net if they want to be able to constrain this population. Okay. Recently, we put some eyes in the forward direction, so we actually know a little bit about what's happening, both in the forward and in the backward direction, if you want to call it that. Okay, so I'm going to be highly biased here to FASER. I'm on the experimental collaboration, but I'll be talking about some other ones as well. So FASER, here's a picture of it right here, is sitting about 500 meters from the Atlas interaction point. Here's Atlas, and 500 meters down is FASER in some random tunnel that happened to be there. In between the Atlas interaction point and FASER, there's about 100 meters of rock shielding to sort of filter away any noise that I don't want to deal with. And then much closer to the interaction point is another experiment called LHC-F, which I'll talk about a little bit. What can FASER do? It's a decay volume looking for long-lived particles, and there's also an emulsion experiment looking for scattering signatures, so neutrinos and dark matter.
Where's the beam axis in this picture?
Right here. So the protons are coming in right here and colliding right here. So FASER is sitting right on the beam axis. You can see there's this trench that's dug out here to be perfectly on the beam axis. Okay. On the other side is SND. Here's a picture of SND. It's slightly off axis. There are some benefits to being off axis. You can ask me about that if you're curious. Okay, but both of these have been taking data since the beginning of run 3. FASER's done a lot so far. We've looked at some BSM models. So dark photons have been constrained. This red line is the relic target for some somewhat tuned parameter space to get some coverage right there. Look for B-L gauge bosons, a whole host of axion-like particles. The first direct observation of collider neutrinos was made. And we've also measured the cross sections for nu mu and nu e. So we're doing quite a bit. I'm going to be thinking a lot about what we can do with neutrinos. So we'll talk about this much more. Okay, but the point is, in just a couple of years, so this was the pilot detector in 2021, and then 2023 and 2024 for all the rest, we've constrained a lot of BSM models and done a lot with neutrinos. And there's much, much more to do. So by the end of run 3, we expect roughly 1600 nu e, 8500 nu mu, and 30 nu tau. And 30 nu tau is a ton. We've only observed 9 at Donut and 7 candidates at IceCube. So depending on how you count, we'll triple or double the population of nu tau. Okay, along with the first observation of nu tau. Okay, on this middle plot right here, I'm showing the uncertainties for each of these fluxes. And the uncertainty in the interaction is really dominated by this flux uncertainty. And this traces back to the fact that I don't know what that forward hadron flux looks like. We really want to constrain. That's extremely important. On the lower panel, I'm looking at how much is coming from charm. As I mentioned, charm is really important for IceCube for that isotropic neutrino background, as well as if I want to constrain the gluon PDF. So new taus exclusively come from charm. New e's have a large fraction that comes from charm, and new mu are sort of diluted by the pion contribution. Okay. So by the end of round 3, we'll have lots of neutrinos to look at, lots of BSM studies to do, but it's really only the beginning. What we really want to do is to complete this proposed forward physics facility. And what this would be is a dedicated cavern to house a whole bunch of experiments. These experiments will be much bigger, so upgrades for FASER and FASER new from 1 ton to 20 ton, and these are some of the interaction rates for neutrinos that we expect. So 10,000 new tau, if we can build this thing. This would be in some field over here. There's actually, I should have taken a picture, but there's a little flag in the ground where it would be dug if it goes through. Okay. In addition to FASER and FASER new, there'll be a liquid argon detector called FLARE. This has some interesting connections to DUNE, which also uses liquid argon. And there'll be a third detector, Formosa milli-charge particle detector. Okay, so we could do quite a bit with FPF. Really due to this large luminosity and target mass, we have an extremely diverse range of studies. So if I want to look for new particles, neutrinos, QCD, astroparticle physics, or dark matter, there's a whole family of things we can do. Please ask me about some of these things. I can talk about any of them. This is from the white paper if you want an extremely thorough review of forward physics at the LHC. Okay, so what I want to do is I want to look at some standard model and some BSM cases in more detail. So I'll be thinking a little bit about neutrinos, a little bit about PDFs, inelastic dark matter, and quarks. Okay, so let's first talk about the standard model case. But before I do, maybe I'll pause for questions. Is everything kind of clear? What's happening? What do you think?
What's LHCF?
LHCF is LHC forward. I'll talk, it's actually the next slide. Looking for neutral particles. Can't really do BSM or neutrino studies there because there's just such an intense flux coming in. But we'll see more about that. The original motivation was for cosmic rays. Okay, so perfectly timed question. So LHCF is measuring neutral particles, much closer to the beamline. Okay, so before we did anything, before FASER saw anything, we want to know, what does our cousin up the beamline see? Can we learn about what we expect to see down here by what we see upstream? Okay, this thing's kind of in the way, but I hope you can see. So the generators, the event generators really cannot describe the forward flux at LHCF very well. So on the left panel, I'm showing the spectra for pi zeros. On the right panel, I'm showing the flux for neutrons in some bin of pseudo-rapidity. Okay. And so what do we see? Well, we see that default generators like Pythia predict a much harder pion spectra and a much softer neutron spectra, sort of a deficit. So if I want to do anything, if I want to learn about astroparticle physics, if I want to do BSM studies, I've got to have a good understanding of the flux, or if I want to even do neutrino cross-section measurements. So the first thing we wanted to do, and this is very important for the muon puzzle, because we really want to know what pions and kaons are doing. So before any phase measurements, we really wanted to tune Pythia to LHCF data. I won't go into too many details on how we do this, but it sort of has to do with what's called the beam remnant. So you can think of a proton-proton collision. It's a bunch of bag of partons. In some collision, Pythia models this by removing some parton that had some hard scattering event. And then the beam remnant keeps going forward, hadronizes, and gives me a flux of particles that I then see at LHCF or at FASER. Okay. So if we tune parameters in Pythia with regards to this beam remnant, we can maximally affect forward physics and minimally affect central physics. Because we don't want to spoil Pythia's success in the central region. So if I go through all this, and please ask me more about this, but the long story short is that you can do much better with respect to the predictions in the forward direction. So now I can have a little bit better understanding of what the pions are doing, a little bit better understanding of what neutrons are doing, with some caveats we still want to do even better. Now I'm not showing it here, but this doesn't spoil the success in the central region, so that's a good thing. And further FASER data will further pin down this light hadron flux. In particular, So if I look down here, this is from a recent FASER paper. This is basically, think of this as the number of pions, and this is the number of kaons. Here's where all these generators live, including our tune, and here's where the data lives. So there's still disagreement. We still want to improve this soft QCD model and these generators so that we can say something useful. And this has, as I keep saying, this has important consequences for cosmic ray physics. So this is becoming part of a broader effort to jointly tune these generators in combination with accelerator and with cosmic ray data. Okay, so you can read a little bit about this in a recent review, but we can use extended air shower information to better improve that model. Okay, so now we have a better understanding of what the hadron flux is doing. So now we have a better understanding what neutrino flux is doing. So now I want to use these neutrinos to probe proton structure. Okay, if you study neutrino physics, you've probably seen this plot 100 times. At high energies, the fraction of the cross-section from DIS, deep inelastic scattering, takes over and dominates the cross-section above 100 GeV. In the spectra I showed a little while ago, the flux at FASER is peaking at about TeV. So we're going to use these neutrinos to probe parton structure, and this will turn out to have huge impacts for central LHC physics. And sort of the intuitive picture, if I have a better understanding of what this Q and Q bar are doing in that proton collision, then I can have a much better understanding of what's going to come out. Okay, so that's the intuition, and I'll show that more concretely here. Okay, so neutrino DIS, just to review, we have some neutrinos coming in with a TeV. They're going to scatter and give off a muon. I'm only using muon neutrinos here because that's the dominant flux, but I could have done with nu E or nu tau. You probably wouldn't want to. And I also could have used the muons that are going in the forward direction for neutral current DIS. Okay, so what we want to do is we need to reconstruct these quantities, the momentum fraction x, the momentum transfer q squared, some neutrino energy E nu. Okay. And we do this by reconstructing these by looking at some observables, including the muon energy, the angle that it scatters out with, and some hadronic energy. Okay, so from this, we'll have some momentum fraction of the collision of the cladding parton and some momentum transfer. And the goal is to sort of cover in this x and q squared space. To say this a little bit more concretely, if I write the cross-section in terms of these so-called structure functions, which are really just PDFs under the hood, the goal is to measure the interaction rate across the x and q squared space, at least as much as I can do, in order to learn as much as I can about the parton distribution function. Okay. So let's look at what this kinematic coverage looks like. So on the y-axis, I'm showing q squared. On the x-axis, I'm showing momentum fraction x. And each little colored point here means I have a significant event rate in that bin. Okay. So this dark shaded region, this is all the old fixed target experiments, all the old beam dumps. Okay. And these colored points are all coverage from the FPF, Fort Physics Facility. And as well as the electron ion collider, it's not showing up very well on here or at all, but there's a shaded gray region along basically these colored points. So the electron ion collider is this other big billion-dollar experiment that's being built right now, and there's complementary coverage with the FPF. So why can we probe such small x and such large q squared beyond existing beam dumps? It's really just that energy. That large neutrino energy allows me to probe very small x and larger q squared. Okay. Now, why would I want to do this if I have a dedicated billion-dollar experiment that's already designed to measure nuclear structure? Well, it turns out that there's a really important degeneracy. And to spell this out concretely, imagine I just have a 2-quark model. For a neutral current scattering for an electron off an ion, I have some linear combination of quark PDFs, UU bar, DD bar. Okay. And given a rate, I have some degeneracy. I can't tell how much did U contribute, how much did D contribute. I have no way of untangling that. Okay. But the charge current at the FPF relies on some different linear combination, U bar plus D. Okay. So by measuring both, we can have some orthogonal information to better reconstruct what these PDFs are doing. Okay, so we do a whole simulation. We simulate many events at the FPF and include this directly into a global PDF fit. This global PDF fit houses a whole mess of older experiments from Hera to, I don't know, experiments that I don't even know. Okay, so let's look at how good not to be. Okay, so here's the PDF fit. On the y-axis, I'm showing the PDF uncertainty as a function of the momentum fraction x for a fixed q squared. This green and well, this larger band right here is sort of the baseline. That's the existing PDF constraint. And this blue that's hiding in the background, this is what you can do with FASER new 2. Turns out that FASER new cannot constrain PDFs. So I can constrain PDFs by a factor of 2 or so, depending on where I am. That's very important, as despite this wealth of data from older experiments, I can still manage to improve PDFs, and that's a very nice thing. So this is for the up quark. We can ask what this would look like for the gluon. Naturally, I don't get much improvement here. The only reason I get any improvement is some second order effect. If I know what the quarks are doing, I know they must sum to the momentum fraction, so I'd have some idea of what the gluons are doing. But I shouldn't expect to see a huge improvement in the gluon PDF because neutrinos aren't charged under QCD. But as I mentioned, the gluon PDF can be probed in other ways. Okay. Now, if I look at the strange quark, I see huge improvements. The strange quark is relatively unconstrained compared to the other quarks. And we get very large improvements by looking at neutrino scattering in the forward direction. This is really important for LHC production. There's a nice paper from 2012 that looked at this. And basically the reason is because these strange quark PDFs are so uncertain, if I want to ask what does Drellian production look like at Atlas, for example, I have a not very constrained picture of what that collision looks like. And why do we do so good? Well, it's really coming from something called charm tagging that I'll talk about in the next slide. Okay, so if I imagine some new mu coming in, scattering off a down-type quark, predominantly an S, then I'm going to expect to see a charm quark coming out. And I can actually tag that charm quark through a couple different ways. Roughly how you can do it is that you look for some kink, and because FASER has this micrometer resolution, you can actually tag and see that there's a charm quark produced in that event. There's other ways you can do it. You can also look for a dimuon signature. Okay. Now this tagging really allows you to precisely know that you scattered off a down-type quark. As a Cabebo mixing, if I see a C, it was probably an S that scattered off. So this tagging has similar effects if I want to look for tests of lepton flavor universality. I want to make sure new E's, new mu's, new tau's are all behaving the same way. I look for trident processes. I don't want to draw the diagram here. Or I can also look for new tau's, where I use that similar technique to look for some kink in the emulsion. Okay. Now, if you don't care about PDFs, like I didn't many years ago before I learned about how important they are, I hope you should. Because what can I do with PDFs? I can understand what is going on at the LHC. So if I think about some standard model processes, just two example processes here, Higgs production and Z production. On the lower panel, I'm showing the uncertainty in the cross-section without FPF data, so using that baseline PDF. If I include statistics and statistics plus systematics with FPF data. So I get good improvements on the cross-section uncertainty. So now I can do precision measurements of electroweak boson production. Basically anything that's some QQ bar initiated process and have a better handle on what's going on. Okay. On the BSM side, there's a lot I can do too in the exact same way. So some people took our PDF and performed a very nice study. If I have some W prime, that's 13.8 TeV, I get some destructive interference if I want to look for this quantity ml nu. Right? And that's sort of what this dotted line is. This is what I should see. However, if I use the same data to look for this BSM signature and constrain my PDFs, and those PDFs will just absorb that signature. That's what this red line is showing here. So this is the observation with respect to the standard model. And I see that I would mistakenly think that I am observing the standard model because I've absorbed that effect into my PDFs and I can't really see the BSM hiding in there. But if I have these orthogonal measurements that allow me to constrain the PDFs over here and look for BSM over here, then this is what I expect to see, this green band right here, outside of the uncertainties from PDFs. So now I have a good handle that some BSM was produced here. Okay, so this is some of the standard model stuff I wanted to talk about, a little bit of BSM. I'm going to now go on to some BSM stuff that we can do. Okay. But maybe I'll pause here for any other sets of questions on the standard model. A lot more fun if it's interactive. Okay, so BSM, what can we do with the BSM? The exciting stuff. Okay, so we've already talked about the standard model, cosmic rays a little bit, kind of on the threshold between standard model and BSM, depending on what you're interested in. But for BSM, we can probe light and heavy physics, which I'll talk about. Okay, what is one of the best things we can do? Inelastic dark matter. Inelastic dark matter, if you're thinking about it, you should generally be thinking about looking for it at colliders. If direct detection, of course, isn't going to do you very good. I've got some mass splitting and the dark matter is non-relativistic, so I don't have enough energy to upscatter into that heavier guy. Okay. And I should mention inelastic dark matter, if you're not aware, just some general model where I have some off-diagonal coupling that interacts with the standard model. So direct detection is not going to work because I've suppressed kinematics, and indirect detection is not going to work because as long as the heavier guy, Chi1, is not too long-lived, I'm not going to have anything to annihilate into. Okay, so direct detection is suppressed as long as I have a suitably large mass splitting, and indirect detection is suppressed as long as the first one decayed quickly enough. So this is a general type of model. Let's look at one realization. And I'm looking at this realization because it has a particularly important consequence for production in the forward direction. Okay, so I'm going to think about this magnetic dipole interaction. It looks like this. So I have some Chi1, some Chi0 that interacts with the photon through this dimension 5 operator. Here's the decay rate of this guy, and I'll flash this on the screen a couple times, just keep this in your mind. This delta is just some fractional mass splitting. It's the difference with respect to the mass of the dark matter. I naturally get a very long-lived coupling, or long-lived Chi1, if I have very small couplings, parameterized by this lambda inverse, or if I have a small phase space. So as that spectra becomes very compressed, I'm going to get a much longer lifetime going like the delta to the cube. Okay? So how do I produce this thing in the early universe? Well, you can go through the usual freeze-out story. I can go through co-annihilation. In this case, this is going to be dominant for small deltas, and it's going to go like lambda. But as I start to make that separation between the two dark states larger and larger, I need to rely on annihilation, and that's going to go like lambda to the -2. So this will have important consequences when I show you the freeze out in a little bit. Okay? But bottom line, the smaller the mass splitting is, the larger coupling I need for the freeze out abundance. Okay, how do I produce it in the lab? Well, we've talked about this. So on the y-axis, I'm showing the effective number of dark matter going within FASER's line of sight as a function of the mass for each particle species. So I'm getting lots and lots of production decaying from each of these hadrons. It turns out vector mesons are very important. You don't produce a lot of vector mesons as compared to something like a pion, but you get some mass enhancement from this dimension 5 operator. Okay, so the heavier the meson, the more preferentially it decays into the dark matter. You can also have Drell-Yan production, and Drell-Yan is important as compared to lower energy beam dumps here, because I have some large center of mass energy available. So in principle, I could produce heavier states through Drell-Yan and not have to rely on these kinematic shutoffs from the meson mass. Okay. Now, I mentioned the small phase space. There's an extremely important detail that comes out of this small phase space. So I've got some photon in the final state that can be made arbitrarily soft as long as I crank down that mass splitting between those two states. So in the rest frame of the excited guy, when it decays, its energy looks like an MEV with this dependence on the parameters. Okay. An MEV, as far as beam dumps go, is a pretty low energy photon. Most experiments required order GeV energy deposits. So if I'm thinking about experiments like E137 or LSND or any of these older beam dumps, CHARM, NuCal, they all have order GeV energy threshold requirements. Okay, but the only way I'm going to get a GeV photon out for such small mass splitting is if I have some tremendous boost. So at FASER, for example, I have a TeV coming out, and that's going to give me a gamma factor of like 1,000. So I can really boost this thing to become visible at FASER. Okay, so let's look at some results. So on the left side, I'm showing very, very small mass splitting. On the right side, I'm showing a larger mass splitting and the parameter space of the coupling as a function of the mass. The relic target that we want to cover is this dashed gray line right here. That mobility of the target line is due to this annihilation versus co-annihilation. As I start to increase that mass splitting, I require larger couplings. Larger couplings. Okay. Now, the main competitor that we should be thinking about these days is SHIP. SHIP is approved. It's a 400 GeV fixed target, and it's looking for all kinds of BSM signatures. But if I take the same threshold, if I require the same threshold at both experiments, SHIP doesn't do so well. So here, SHIP, I'm taking a sort of optimistic energy threshold of 300 MeV for SHIP, and it's able to cover some of the relic line. And if I take that same threshold for FASER, of course, I can cover much, much more. Okay. At larger mass splitings, SHIP will take over, but this really lends to a very nice complementarity between the two experiments. FASER can look for very soft signals that were boosted to become more visible, and SHIP, due to its tremendous luminosity, can cover the rest of the space. Okay.
I'm confused by something. I thought you said that the reason that beam dumps couldn't do as well here is because of the threshold.
Indeed, yeah.
So sorry, but now you're saying that if I take the same threshold for SHIP and for FASER, FASER does substantially better for some values of the mass split. So I think I must have missed something.
I mean, the statement is for very small mass splittings, you know, I can imagine, let's put it this way. If I didn't take such an optimistic energy threshold, SHIP would be gone. SHIP wouldn't be on this plot at all. If I looked at smaller mass splittings, SHIP would be gone.
Okay.
Right? 5% is, let's call that a relatively large mass splitting, such that I can easily cross a threshold of 300 MeV, GeV, 3 GeV, or et cetera at SHIP. SHIP has a huge luminosity. If I shoot you can start to see also other beam dumps start to come in here. So this is NuCal and CHARM. So they start to come in for whatever their energy deposits are, or GeV.
Here you consider dipole interaction. I remember correctly, which break the chiral symmetry of this fermi. While you have very light fermi here.
Mm-hmm.
Do you have some UV concretion to generate this interaction?
You can get it a couple different ways. I mean, if dark matter is composite, then I would naturally expect some sort of dipole interaction. You can also get it if I have like some Majorana mass or some like pseudo direct pair. You can get some mass splitting for a dipole type interaction.
But I mean, like in some of the papers that realize this, you would integrate out a scalar and a fermion that have electromagnetic charge, and that those things have like Yukawa couplings to the dark matter core component.
Yeah, but my worry is that here the dipole interaction violates the chiral symmetry. So I wonder if you consider actually UV compression and compute the quantum correction to the mass of this fermion. That might be actually too large.
It might be. It's not something I thought about before. It's a good question, though. We should talk after. Okay. So in elastic dark matter, we can do very well. So this is just one example of FASER probing GeV scale physics. But FASER can also probe heavy physics on the scale of TeV. There's sort of another weird quirky signature that happens to go in the forward direction, namely quirks. So if in some models of neutral naturalness, I have some top partner that's charged under some mirror QCD-like symmetry, sometimes called infracolor, and I can have some hierarchy where the mass of the lightest quark is heavier than the confinement scale. This is opposite to the quarks, of course, where there exists a light quark that is below the confinement scale. What is the important consequence? Well, for quarks, we're sort of familiar, right? I have some quark QQ bar pair separating. And I have some energy stored between them in the form of a color string. Eventually that color string stores enough energy to pop more quarks out of the vacuum. And that's how we get what we call hadronization. But for quarks, the situation is not the same. So here I can have some quark bar start to separate, but the energy stored in that string will never be large enough, or rather will be suppressed in order to produce a quark pair produced between them. So I don't get any sort of hadronization, and I get this crazy signal where these quarks go out and oscillate back and forth. So it turns out if you want to look for this in Atlas, you can't do it. And the reason is they have these very sophisticated tracking algorithms, and they all assume that I have some helical trajectory. So now if I have some long range interaction that sort of gives me something that's highly non-helical, I'm not going to reconstruct a track. I'm not going to be able to correspond to any types of energy or any kinds of direction with some charged particle. But I have these heavy particles that I can't see at Atlas. Okay, but if I have, if I think about pair productions, think about QQ bar goes to QQ bar, they're going to be produced with the net PT of 0. And because I have this stable infracolor string, they're just going to drift along in the forward direction without ever even intercepting Atlas. The only way they can intercept Atlas is if I have some initial radiation to throw me to high PT. But without that, at leading order, it's just going to go right down the beam pipe without ever intercepting the Atlas tracking layers. Okay, so this was some work by these people that first thought about this. Here I have some quark trajectories, and 480 meters down the beam line past this rock, I have FASER sitting there that can then look for these types of signatures. What would it look like? Well, I can reconstruct this oscillatory track in FASER, or I can look for signals that are out of time with the collision. So these are TeV scale particles. They're going to be drifting along very slowly, highly non-relativistic. So if I see some collision that took place somewhat long after a collision at the LHC, then I can know that something strange just happened. Okay.
Sorry, I have a question.
Yeah.
What's the amplitude of these oscillations?
The kinetic energy of them coming out, right? So if they happen to be produced highly exceeding the threshold, they're going to be thrown out, and then also the confinement scale. As I start to turn up that confinement scale, I'm sort of keeping a strong infracolor force binding them to one another. Yeah. So there's a whole range. So that's a good question. So at Atlas, you can probe quarks. If you imagine I have some, kilometer scale oscillation, then it's just going to look like tracks that are mostly straight and affected by the magnetic field. I can look for those. If I have very tight oscillations, then I'm not going to resolve this non-helical pattern at Atlas, and I'll just see some heavy stable charged particle, which I can look for again. But when those oscillations are on the scale of the detector, Atlas is blind.
Just a quick question, is there a limit on the actual scale of these oscillations? Like off of the theory bound itself, or?
I wonder, so people have thought about, or people have at least somewhat published about like even meter long or like kilometer long oscillations. So that would be very, very slow confinement scales. I don't know of any theoretical or fundamental limit you'd run into, but take that with a grain of salt.
Thank you.
Okay. But nevertheless, I'm going to get predominant quark production going in the forward direction. So people thought about this FPF at the LHC, and then we thought about it for the FPF at the FCC, which is a whole another hour-long talk I could talk about. Okay, but if I think about how much of that space and that confinement scale and that mass I can cover, here's some of those heavy stable charged particle searches at Atlas, some monojet searches where I don't reconstruct the track, but I have some initial radiation. We can cover quite a bit of space for the FPF at the LHC, up to about 500, 400 GeV or so. And if you go to the FCC, well, I've just got tremendous energies, so I can start to approach 8,000 GeV or more. Okay, so FASER at the FCC-HH is a whole other program I could have talked about. There's much more you can do. We've also thought about putting forward detectors at a muon collider, and there you just have ridiculous event rates for neutrinos. Please ask me about these things. I think the moral of the story that I would like to keep in mind is whatever detector we build, there should be some forward detector component. Because you really want to make the most out of it. And these detectors don't need to be big. They just need to be small. You know, FASER is the size of this little length right here, and it's able to measure things and look at LHC collisions in a way that no other experiment can. Okay, with that, I'll sort of summarize. So in the forward direction, we have a rich neutrino program. We can look for new taus and new tau bars. Important connections to astro. That's coming from that square root of S and that center mass energy, boosting to a frame. We can probe QCD new regimes for very small x. Important consequences for a whole bunch of experiments. IceCube and KM3net, PROJ, Atlas and CMS, Dune, EIC, and more. The more measurements we make in the forward direction, the more we can help out these other experiments. And there's a diverse range of BSM, long-lived particles, stable particles, neutrino BSM, and much more. Thank you very much.
Questions for Max?
In the Pentagon, you have like inflaton.
Yeah.
Did you have one?
People always ask about that one. So there are some motivations for a light dark Higgs that can play the role of an inflaton. What's the mass scale? Like order 5 GeV, 10 GeV, sort of down there. In dark Higgs, you have very nice sensitivity. It's naturally long-lived. So from B decays, I can have this dark Higgs coming out. So that's the connection.
And it is like it has this Higgs portal coupling or something.
Exactly,
Okay.
exactly.
And this is like low scale inflation naturally, or
I can't remember the details on that. Yeah. Probably. Yes, actually, it is. It has to be, yeah.
okay.
But does it have to be? I mean, like you could separate out the part of the potential that tells you what its mass is from what the potential is doing at large field excursions. So like if I don't care about tuning or where this thing comes from, I'm imagining some sort of like inverted top hat where I have some very small mass that's telling me what it's like, or you know, there's some m squared phi squared, but then at large field excursion, I could go out to the Planck scale, I could have the overall height of the potential be high. If you're willing to just factorize those things.
At the price of fine tuning, I guess?
Yeah.
Probably. Yeah, that's a good question.
I mean, they're scalars, so like, you know,
We're gonna be stuck with it already, right?
I mean, I bet you could do this without introducing a whole lot of new fine tuning, like something in like a hybrid inflation model, I think could do something like this. I'm not sure.
yeah, you might be.
Could you go back to event generator?
Mhm.
And the beginning of section 2. Yeah. And maybe next picture. Next one. Yeah. When there's still a big deviation. In the second picture, big deviation. Yeah. Big. Yeah.
Why is there?
Yeah.
Fundamentally, I suppose there's sort of two reasons. One, I think, okay, the short answer is we sort of tune the parameters within some realistic values. So there's some parameters regarding the beam remnant. Possibly if I extrapolated them to regions that I think are not so feasible or realistic, you know, much higher than the GeV scale, where I don't really expect a lot of this QCD modeling to take place. Maybe I could have done better, but we kept guardrails on the fit so we don't do anything too crazy. So that's at least one answer. But the more likely answer is that we're probably just not modeling QCD correctly. I could have done this similar study with the other event generators. There's a whole host of them. None of them can really reproduce the spectrum. And they all have slightly different ways of dealing with things, you know, either string models or Reggie theory or whatever, and none of them can really reproduce this. So it, I think, points to just sort of an inherent QCD mismodeling, something we're missing. There's programs to try and improve this machine learning program, ML-HAD, and there's also another one, HAD-ML. They're using machine learning to try to get a better grip on machine learning, or on hadronization. Oh yeah, indeed. There's more to be done. We really want to improve this.
Could you remind me how low you can go in the splittings?
For inelastic.
Yeah.
I mean, the only thing that would happen, as I start going lower and lower, eventually I'll run into a couple of things, right? That photon will start to become really soft. So if I went another order of magnitude, I would be sitting, so this would boost it to a GeV. So if I want another order of magnitude in delta, now I'm talking 100 MeV or so, and then it becomes questionable about how well I can resolve this. But if you could resolve arbitrarily soft signatures, then I want to keep this delta above 10 to the minus 6 for direct detection. But otherwise, I don't see any showstoppers.
Maybe I have one more question.
Please.
So I guess sort of a general question I had that you at least partially answered right here is in what scenarios should I prefer, or in what scenarios does it do things like FASER or the FPF have an advantage over beam dumps? And so there, of course, you've shown one example, and I guess I wanted to wonder if there's like other cases that you know of, or like some general principles for where you do better than beam dumps.
There's sort of two general principles that we've been keeping our eye on. So one is this boosting soft signals to become harder signals. The other, I sort of alluded to, corresponds to this large center mass energy. So for example, in a more vanilla inelastic dark matter model with a dark photon, Drell-Yan production turns out to be very important there. In principle, for Drell-Yan, I can probe, I could have TeV scale going in the forward direction. The PDFs are going to kill me, but nevertheless, I have access to that. It's just a matter of luminosity at that point. Whereas a beam dump, on the other hand, is completely impossible to attain this. So those are sort of the two on my mind. There are, for the long-lived particle searches, you can also think about secondary production throughout the infrastructure, intervening FASER and, show a slide, in between FASER and the interaction point. So there was a whole other thing we thought about. So people don't usually think about muons, but as a muon is produced near the interaction point, it's able to go through all this junk in between. There's some absorbers, some rock, the experiment itself, and anywhere along here, I can produce some BSM. So it's just some muon Fieg scalar, but you could adopt some similar philosophy. So for long-lived particle searches, those are the things that come to my mind. For neutrino BSM, you're not going to produce a lot of new taus at any beam dump. So anything I want to do with new taus, you should really think in FASER. I don't know if this is a controversial statement or not, but if you want to see new taus, I mean, you got to dig through that at IceCube, or you got to look at FASER or SND.
Thanks.
So what about heavy neutral leptons? So like you're making a lot of neutrinos, right? And there may be a couple of different ways you could go about observing them here. One is they're long-lived particles that you make at the interaction point and they decay. Another possibility might be that you sort of produce them from the mixing inside of FASER.
Yep.
And then they decay promptly. And so you could sort of like imagine two different.
I can also do a very vanilla oscillation experiment for 10 EV, 50 EV scale sterile neutrinos. If I look very closely at the neutrino spectra, if I have this 10 EV scale sterile neutrino, I'm going to see some wiggles that correspond to that oscillation. You can do this. There's a very nice plot that unfortunately I didn't attach. But yeah, indeed, you have the right idea. Otherwise, I can produce it. I can look for some long-lived particle decay. That's the idea.
All right, if there are no more questions, let's thank Max again. Very nice.
Wait,